Alright, for topics 1 through 4, I will be doing Sinova Heron's problems. So in question 1, we have part A that includes buoyancy, and there's a little toy submarine, and it wants us to find the buoyancy force on the submarine. So we can assume there's constant density, constant acceleration due to gravity, no work, no friction, and our properties come from the common units handout. We can find the submerged volume by using this equation right here, where the weight of the submarine equals the weight of the displaced water. We get a submerged volume of 0.0018 meters cubed. We find the buoyancy force using this equation highlighted here, and we use our density of our water, our volume of our submarine submerged, and our acceleration due to gravity. And we get a buoyancy force of 1.7658 newtons. For part B, it uses hydrostatics, and this time it uses the submarine in the world's deepest swimming pool at 148 feet below the surface, and we need to find the total absolute pressure. So we can assume constant density, incompressible liquid, no change in G, no work, and no friction, and our properties come from the common units handout. We first have our P absolute equation, where P absolute equals P atmospheric plus P gauge. We need to solve for our P gauge because we already know our P atmospheric. Our P gauge is solved using this equation, where is the density of the water times G times the height that the submarine is under the water. So we get a P gauge of 442,533.024 pascals. We then solve for our P absolute using our equation from before, and we get an absolute pressure of 544 kilopascals. In problem 2, we use topic 4, macroscopic momentum balance. So we have an industrial fan connected to a chair, and the kid sits on the chair and floats above the ground. So the problem wants us to find the exit air velocity needed to equal the mass of the system. We can assume no mass change in system, no velocity entering, no change in G, and our properties come from the common units handout. We start with our momentum balance, as seen here, and expand it out. The dv dt can actually be canceled out because there is no acceleration, and the dm dt can be canceled out because there is no mass change in the system. We then use our simplified momentum equation for F of air, and we get F of air equals m of system v exit minus v enter, but we know there's no v enter, so it's just m system times v exit. We then use our force balance, which is given here, and our acceleration is 0 because the system is in balance. We get a weight equals F of air, or equals m system v exit. We then substitute in our mass for this equation as seen here, where m of our system equals the density times area times velocity of the exit. We get our weight equation as seen here. We then rearrange that equation to solve for our velocity of our exit air. We then solve for our weight using our mass total times our gravity, and we get 222.08 IBF. We then solve for the area using this equation, and we get 3.14 squared feet. We then solve for our exit velocity using the equation from before, and we get an exit velocity of 170.87 feet per second. The past 3 problems have properties that are cited here. So topic 3 is actually involved in a 4-part problem where there is a dam and water is being released from a reservoir into a dilute discharge from a Wallace sewage treatment plant. Okay, so part A asks us to use topic 5 to figure out if it's laminar turbulent. Part B actually wants us to use the same topic to solve for the friction factor. Part C changes part of part A and wants to know if it's laminar turbulent again and what the friction factor is. Alright, for part D, we use topic 3, which is extended Bernoulli, and we actually have to use the friction factor calculated in part C, and we need to use that to calculate the pressure loss due to the friction between the 2 ends of the horizontal portion of the pipe. For this question, we can assume constant density, constant G, no change in Q, incompressible fluid, steady state. We get our properties from the common units handout. So we start with our extended Bernoulli equation, which is actually right here. And this equation shown right here is after the density has been multiplied through the entire equation. And we have our friction loss here. And our friction loss is actually equal to our friction head loss times the density times G. The friction head is actually here, where it's the friction factor, the length, the velocity, the diameter, and acceleration due to gravity, and we substitute that into our friction in the pipe equation, and we substitute this equation back into our Bernoulli equation. Finally, we apply all our assumptions to the Bernoulli, so it's steady state, Z1 equals Z2 because it's horizontal, and V1 equals V2 because of continuity, and then we simplify the Bernoulli equation based on those assumptions, and we get delta P equals our friction loss. And we can solve for a delta P, which turns out to be 1.53 kilopascals. For topic 3 properties, they are cited right here in citation 11.